All right, 12.4, Infinite Geometric Series, Day 2. So if you remember from Day 1, we did partial sums. We actually added each term together, the first term plus the second term plus the third term. We kept doing that, and we saw one example where because each new term was getting smaller and smaller, as we added them, it didn't seem to matter as much eventually, and we realized that that sum was getting closer and closer to a value. We saw another one where each new term was just bigger, 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 so every time we added one, the sum got even bigger, and we said this really isn't heading anywhere, there is no sum here. So we're dealing with the same stuff today, but instead of using partial sums, where you actually had to go one term at a time and add the first term and the second term and so on, we're now moving on to the formula that will be much more efficient. So you see it's still all about the common ratio though, that if the absolute value of the common ratio is less than 1, proper fractions, decimals less than 1, etc., then you can find a sum using this formula. On the other hand, when the common ratio is greater than or equal to 1, remember that means you might be multiplying by 2 each time. That means each term is getting bigger. And if each term is getting bigger, when you add it, then the sum gets even bigger. Well, then you're not heading anywhere. You're just getting bigger and bigger. There is no sum to mention. So let's go ahead and try our first example, noting that in the formula, the two things that matter are the first term and the common ratio. If we know those two things, we're in business. So first example, the sum from n equals 1 to infinity of 5 times 0.8 to the n minus 1. First thing we're going to identify, what is the common ratio? Well, the common ratio is what you multiply by over and over. That's the exponent, that's the base of the exponent, that's our common ratio, it's 0.8. Now I check, and because 0.8, absolute value, is less than 1, I'm going to use this formula. There is going to be a sum for this. So I go ahead and that tells me I also need the first term then. If I'm going to find the sum, I better get the first term. So I'm going to evaluate what happens when n is 1. That's what happens first here. So it's 5 times 0.8 to the 1 minus 1. Of course, 1 minus 1 is 0, so that's 5 times 0.8 to the 0. Anything to the 0 power is 1, so that's actually 5 times 1. And anything times 1 stays the same, so the first term is 5. So now I can go ahead and do the sum. The sum is, and I'm looking at the first term, well, the first term is 5, divided by 1 minus the common ratio. 1 minus the common ratio is 0.8. And if I do 1 minus 0.8, I get 0.2. If you do 5 divided by 0.2, you get 25. So that means if you took this first term of 5, if you found the second term, and the third term, and the fourth term, and the fifth term, and if you added them together, and if you just kept going, you'd see your sum getting closer and closer to 25. And that's if you go infinite forever. You just keep getting closer to 25. You never quite get there, but you'll get infinitely close, like 24.9999999. So we say it's approaching 25. Next example. Here we've got our next sum. You can see all the critical values here, where we're starting, what the common ratio is, etc. And so it starts again with identify the common ratio. Well, right there, the base of the exponent is 5/4. Now I stop and pause for a moment. If the common ratio is 5/4, if 5/4 is bigger than 1, and it is, then there is no sum, and that means each term you're multiplying by 5/4, so the next term is bigger, and when you add it, your sum gets even bigger. And then if the next term is even bigger than that, you just keep on going up, and we can just stop right there. There's no further work to do, because there is no sum. Now the last thing I want to catch here is just something for you to look out for, that while the formula uses a sub 1, that's what's printed in the book, the first term, it's really the first term of your series, no matter where you start. So if we're starting at n equals 0, that's going to be our first term. We're not starting at n equals 1 this time. So in this case, identify the common ratio. It's 2/3. That tells me we're going to go ahead with this problem. It's less than 1, so every new term is getting smaller. So as you add them, they matter less and less. Your answer is approaching something. And then that tells me that to move forward, I need my first term. Well, again, my first term this time is a sub 0. I'm not using a sub 1 for this because we don't start at n equals 1. So I'm going to do 2/3 to the, and for n minus 1 I put 0 minus 1. Well, that's 2/3 to the negative first, and if you remember negative exponents, they flip fractions. So a sub 0, the first term of our series, is 3/2. That brings me to the sum equals. I'm going right back up here. I'm going to put my first term, which happens to be the 0 term, 3/2, over, and then 1 minus the common ratio. And that's right here, that's 1 minus 2/3. So from here, you're just being careful to work this out one bit at a time. That's 3/2 all over 1 minus 2/3 is 1/3. You could always rewrite this as 3/3 if you want. 3/3 minus 2/3 is 1/3. And whenever we divide by a fraction, it's easy to rewrite that as multiply by the reciprocal. So I put, instead of divide by 1/3, I put times by 3 over 1. At this point, go ahead and multiply across the top, multiply across the bottom. We've got our answer. The sum is approaching 9/2, or call it 4.5 or 4.5 if you want. So that's it for today. You're now working on page 823, just 3 problems today. Numbers 13, 15, and 17. That's 13 through 17 odd. Thank you, everyone.